Welcome to Session 9 of Dr. Donald J. Wheeler's Understanding SPC seminar. This session will begin with some examples of using the charts to tell the story contained within the data. The second part will address the computation and use of capability and performance indexes. Here we will see how these indexes collectively tell a story that has often been missed in practice. This session will make use of the Understanding SPC text and the SPC workbook.
Why Susie Can Breathe. An 11-year-old girl with severe asthma who had been hospitalized 3 times in the past 9 months was brought to Dr. Peter Boggs, an allergist. After the usual tests for allergens, Dr. Boggs gave this girl an appropriate prescription and a PFR gauge. PEFR, peak expiratory flow rate. A PFR gauge is a gauge in which you blow as hard as you can, and it measures your exhalation rate in liters of air per minute. She came back in a couple of weeks, and this particular gauge recorded the data. So he downloaded the data, and he took the first thing in the morning, pre-medication, PFR scores, and put them on an XMR chart. Now, her predicted best is about 310, and the upper limit of 322 is consistent with that. The lower limit of 44 is consistent with her medical history. Dr. Boggs says you go below 100, you're going to be hospitalized because you're going to be suffocating in your own carbon dioxide. So the lower limit of 44 was consistent with her medical history. And the average of 183 is only 60% of her predicted best. So this kind of gives you an idea of the status of the patient, pre-medication, first thing in the morning. But the interesting part is the run near the limit, the 4 days, days 9 to 12. So Dr. Boggs asked, what happened here? Oh, that's when she went to her aunt's for the weekend. Aha. So this is when she came home and got sick again. Yeah, she did. He says, suddenly, you give them the allergy test and you tell them this red dot means that you're allergic to your dog. That's clinical. But when they collect their own data and they can see with their own eyes what's going on, it changes everything. So the patient and her mother got busy based on the graph, just motivated them like the other things hadn't, to start working on getting rid of her allergens in her environment. So they changed the floor covering in the bedroom, changed the linens on the bed and bedspread. Her mother quit smoking in her daughter's presence. They got the dog out of the bedroom. Started working to improve these numbers. You see, what the chart did, and this is what Dr. Boggs told me and what I've heard over and over again, this chart changes the dynamic. Now we're all working on the same problem, and the patients are part of the treatment team instead of being the objects of treatment. Discovery and communication unexcelled by anything else. It's so powerful. This also gave Dr. Boggs an objective way to evaluate the effectiveness of the treatment. The 200-point swings from day to day are undesirable. The lower limit of 44 is in the danger zone. We need to move that up. We want to get the average up. So, based on the compelling evidence of the chart, they worked to change her environment. So here we have it, days 82 to 93. The limit is up from 183, the center line is up from 183 to 209, and the lower limit is up from 44 to 134. Significant improvement. 5 months later, the patient's average peak flow of 297 is 96% of her predicted best. She had added 200 points to her lower limit, and she no longer suffered from severe asthma. Now she was doing as well at home as she did at her aunt's, and her bronchodilating medication could handle her asthma. Believe you me, Dr. Boggs hands out PFER scores and draws charts for his patients all the time now. Our next example is also from Dr. Boggs. Jane suffered from rhinitis for 10 years. 37-year-old had this runny nose for 10 years. Thinking it was allergies, she went to see Dr. Boggs. Skin tests showed no evidence of allergen-specific antibodies. So rhinitis must be due to irritants rather than allergens. And as they searched for irritants in her environment, Dr. Boggs decided to use PFER scores just to monitor changes in her airways, even though she did not have asthma. So they started with a 9-day baseline where there were no deliberate changes in the patient's home environment, work, or activities. Next, the patient slept in the living room while they were changing the floor covering in the bedroom, and she did better. Obviously, the problem is in the bedroom. When the patient moved back into the refurbished bedroom, her rhinitis returned and her PFER scores dropped back to the baseline. The search for irritants continued. And they found that the attic access in the bedroom closet was completely open. When they sealed the hole in the closet ceiling, there were no more insulation dust in the bedroom, and the patient had not felt this good in years. Pity the husband of fixing the hole in the closet had been on his to-do list for the past 10 years. You see, process behavior charts provide the feedback that is needed to understand when our actions do not work and when they do work. Not yet, not yet, at last. The next example is in your workbook on page 40 to 42. An acquaintance of mine sent me some data. The number of Category 3 or larger hurricanes in the North Atlantic from 1940 to 2007. So here we have a histogram of the number of North Atlantic major hurricanes. As I said, this is on page 40 to 42 in the workbook. Here we have the frequency. Here we have the number of hurricanes. So 5 years they had no Category 3 hurricanes. 17 years there was one major Category 3 or larger North Atlantic hurricane, and so on. So how many years did we have 2? How many years did we have 3? And so on. Simple histogram. If we try to fit a probability model to these data, we don't have a detectable lack of fit between a Poisson distribution with a mean of 2.59 and our histogram of the data. So from the average of 2.59, we can compute an approximate 95% confidence interval for the mean number of hurricanes per year that are category 3 or larger to be from 2.2 to 3.0. There, we've done our statistics now. Wait, what about bad years? Well, with a mean of 2.6, a Poisson probability of getting 7 or more category 3 hurricanes in a single year is about 1.7%, less than 2%. This means that in 68 years, we should have about 1 year with 7 or more major hurricanes. But when you look at the data here, we've had 3 such years. You do recall we keep having 100-year floods, don't you? Every 10 years or so. This is the way we come up with those projections. However, NOAA researchers felt that these data represent 2 different weather patterns created by natural fluctuations in the tropical climate system, known as the tropical multidecadal oscillation. And you can see this on the NOAA website, story number 184. So here we have a chart. You have this in the workbook on page 41. There are 2 periods, periods of low activity and periods of high activity. The 33 years of low activity averaged about 1.6 major storms per year. The 35 years of high activity averaged 3.5 major storms per year. So which years are properly characterized by the average of 2.6 major storms per year? Think about that really carefully. You see, neither group is characterized by the 2.6. So what period does the interval estimate of 2.2 to 3.0 major storms per year apply? Neither period. Any analysis of observational data that does not begin with a process behavior chart is fundamentally flawed. Just look at the running record. Are these data likely to be homogeneous? Just look at them and you see periods of low activity followed by periods of high activity. Going back and
Dr. Wheeler, so for
Henry.
For historic data like this, so is there a way to group the historic data? Because I see you have breaking points, right, between these 4 groups of data. But when I look back, how do I determine
judgment?
Right? Okay.
I actually did this analysis before I found the NOAA website. And the NOAA website told us there was a break in 1970 and a break in 1994. But I had spotted
I was just wondering if there's
just by listening to the data.
Way to do it.
Pardon?
I was just wondering, other than making observational judgments, is there other more systematic way to group the data?
NOAA had more to go on. They had a lot of other inputs and data to make their call about the 2 different periods of high activity and low activity. But you see, without even any of that knowledge, you can spot this just looking at the data. And part of the secret of the success of this approach is that it helps you to discover things you didn't know. It'll confirm some things you did know, but it will help you discover things you didn't know. And that's the real leverage. You see, just look at that running record and visualize a band that surrounds the running record, and you see that that band has to change width. Data analysis requires the careful and thoughtful interpretation of the data in their context, rather than the unthinking computation of limits or the automatic fitting of probability models and their parameters. Statistics starts with the assumption that a single model exists. SPC starts with the assumption that a model does not exist. The data might be changing. So listen to the data, let them tell you what they can. You'll be surprised what you can learn. Now, someone mentioned a lot of confusion on the internet about SPC, and yep, there is.
I have a question. Sorry,
Yeah, certainly, Anna.
Before you go on, so now you're showing the average value per year, right, of the data that was taken that year. Is there an issue if there is a different number of data points in each bin? Meaning, let's say in the year 70, we collected data for 100 data points, but in the year 71, we collected 10 data points. It still is still okay to do that comparison of the SPC in this way, like?
You can compute limits using as few as 5 or 6 data points.
Right, but your 6 data
expect...
points, if they are a group, right, like that data point is already an average of n number of data points that are in that bin, right? If that n of that bin changes across bins, is that an issue?
They're just individual storms. How many storms happened in any year?
Right, so if in year 40 we have 100 storms and in year 45 we have 50 storms, is that an issue that we're taking the average of them in the bin, the number of data points in each bin?
You're not taking average, you're just reporting it. So in year 40, there was no storms. In year 41, there were 2 storms, for example. In year 50, there were 7 or 8 storms.
Okay, yeah, because we're counting events instead of, yeah, okay.
That's why I like the XMR chart, because it starts off with the running record of the raw data. And on the running record of the raw data, every point has to sink or swim on its own. So when you see the running record of the raw data, you immediately begin to understand what the behaviors of those data are. And if you see something like the graph in your workbook on page 35,
yeah,
you know that you're looking at signals without ever doing computation 1. And that affects how I might choose to compute my averages, how I might divide the data up. Here, I looked at the running record and I said, I'm going to break it here, I'm going to break it here, I'm going to break it here. And that was just a judgment call based on the running record. But this turned out to be a good point to break this time series, because you get the period of low activity and the periods of high activity, which are substantiated by other insight, other inputs, other meteorological data. So it's not just this is an idea, but it's an idea that gets supported from various lines of thinking. And of course, when all the different lines of thinking converge, you're really talking about something that's real. So we don't use these charts in a vacuum. And you shouldn't just unthinkingly throw the data in the computer and get the average. Look at the data first. You've got to interpret your data in context, and the analysis has to be driven by the context, and the interpretation has to be driven by the context. Remember, that's where we started off on day one.
Now we turn to Chapter 6 of the Understanding SPC text to consider the capability and performance indexes. We begin on page 117.
Page 117. Lean production is predicated on the assumption that the fabrication processes will be operated predictably and capably. Go back and read the book by Jones, Womack, and Roos, and 3 times in the book, they say this, in effect. People are running around trying lean production before they get the processes operating predictably, and all they have is more train wrecks. Talk about the process capability in any meaningful manner. We have to extrapolate from the product we have produced and measured to the product we have not yet produced. While the extrapolation is inherently uncertain, it becomes reasonable when we can demonstrate that the process has been operated predictably in the past. So we need to go beyond the capability indexes themselves and understand the relationship between the process performance and the process potential. A process that is operated predictably will be operating up to its full potential. Such a process may be said to speak with one voice, and that voice will be characterized by the natural process limits. So the ball joint socket process was a predictable process. And here we have the chart we originally saw back on page 110 in the last chapter. Predictable, capable. This is 1 week's worth of data. 96 data. At the top of the next page, here's our histogram. The process performance. The natural process limits will go from -1 to 10. That's what the process has done, what it is doing, and what you can expect it to continue to produce unless you intervene in some way. Since the process is being operated predictably, and since it has been predictable for the past 5 months, we can reasonably certain that the natural process limits not only characterize these 96 data, but they also characterize the 20,000 parts produced during this week. So that's the extrapolation you're interested in. All data are historical, and all the questions of interest pertain to prediction. But when a process is operated unpredictably, it will display exceptional variation, and there will be a discrepancy between the past process performance and the process potential. So here we have the first week of the creel yield data. It's unpredictable, isn't it? So we draw the histogram for that first week, and the 3 standard deviation limits describe the process performance, while in the past, and while the 3 sigma limits estimate the process potential. And see, we learned about the difference between method 1 and method 2 last week. And here we're going to make use of that. Sigma x, remember, is method 2, standard deviation statistic method 1, and there's a difference when the process is not homogeneous, when the data are not homogeneous, I should say. So here's another example. It's unpredictable. Shewhart's resistivity data. And when we draw the histogram there, the 3 standard deviation limits describe the past performance. The 3 sigma limits estimate the process potential. So we're going to make a play, a use of the difference between method 2, sigma x, and method 1, the standard deviation statistic. So watershed specifications, page 126 in the Understanding SPC text. You take the minimum acceptable value and subtract a 1/2 measurement increment. You take the maximum acceptable value, add 1/2 measurement increment. And see that you take the 6 minus 1/2 gives you 5.5. You take the 12 plus 1/2, you get 12.5. And when you subtract 5.5 from 12.5, you get the right answer for the specified tolerance. And the specified tolerance is important when you start computing capabilities. Okay, capability. The capability ratio, P sub P, is an index number that compares the specified tolerance with the process potential. The space available within the specifications divided by the space required by the process. Pause here, and for a moment in the textbook, turn back to page 64. We're looking at the picture on page 64 in Understanding SPC. And on page 64, you can see that no process needs more than 6 standard deviations elbow room. 6 standard deviations is going to be sufficient as a measure of the space required by the process. And so we're going to use 6 times sigma x as our estimate of the space required by the process. And the justification for that doesn't require a normal distribution. In fact, which distribution on page 64 goes limit to limit?
Uniform distribution.
Oh, I didn't get there, did I?
Normal distribution.
The normal goes limit to limit, doesn't it? It's the worst case scenario. There's a reason for that. The normal distribution is the distribution of maximum entropy. It is the worst case analysis. It is the worst case scenario. The middle 90% of the normal are spread out further than the middle 90% of any other distribution. So our capability index is the specified tolerance divided by 6 times sigma of x. Page 4 in the workbook. We collected 50 data from the bead board, and we got these 4 numbers. Our subgroup size was 5. We got a grand average of 9.14. We got an average range of 4.0. So that was on page 4 in the workbook. And so when we estimated sigma, we got a 1.72 units per standard deviation. We're going to use these numbers on page 20. For operator 2, up here at the top, N is 5, X double bar 9.14. I'll zoom in on that. And sigma of X is 1.72. So C sub P, upper spec limit minus lower spec limit over 6 sigma of X. Well, now our spec limits were 5.5 to 12.5, weren't they? 12.5 minus 5.5 over 6 times 1.72. So that's 7. $1.72 times 6, 10.32. We'll call it 0.68. Yeah, the space available is 68% of the space required by this process. Let's write that down. Space available is 68% of the space required by process. Bottom of page 127. Clearly, the capability ratio describes the amount of elbow room available to the process. However, it does not take into account the process location. So we're going to compute something called the distance to nearest spec. Operating, the picture is really the most important part, figure 6.10. Operating this close to one of the specifications is like being centered in spaces, the specifications that are twice the DNS wide. So twice the DNS is the effective space available. It's like we're centered in these narrower specs. And so we talk about the centered capability ratio. It's not good language. It's a little bit muddy, but that's what it is. And it's the effective space available divided by the space required. Twice the DNS over 6 sigma of X. Well, let's go back to our example on page 20. The average is 9.14. So which specification is the nearer specification? DNS 12.5 minus 9.14. If my feeble brain is working, this is 3.36, isn't it?
Yep.
So CPK twice the DNS divided by 6 sigma of x. Two times 3.36 divided by 6 times 1.72. So this is 6.72 divided by 10.32. $0.65. How did we interpret that? The effective space available is 65% of the space required by the process. These numbers don't sound super, but if we look at the histogram, we had 5% nonconforming. The best way to estimate the fraction nonconforming is always this way. There have been a lot of techniques invented for estimating the fraction nonconforming, and none of them really beat the 300-year-old point binomial estimate. How many did you look at? How many of them were bad? Form the ratio. Duh. All you need are fingers and toes. On page 130. The most important aspect of the interpretations above is the meaning of C sub pk and C sub p change depending on whether or not the process is being operated predictably. With a predictable process, CP and CPK describe the actual capability of the process, what it has done in the past, and what it can be expected to continue to do in the future. With an unpredictable process, the capability indexes characterize the minimum that you can expect to achieve from a process if and when you learn how to operate it up to its full potential. In most cases, you will do even better. So it's the hypothetical capability of an unpredictable process or the actual capability of a predictable one. The performance indexes are very similar to the capability indexes, but they use the global standard deviation statistic, which means they describe the past process behavior, not the process potential. So P sub P is the space available within the specifications divided by the space used by the process in the past. And we get that by 6S. And PPK, the centered performance ratio, the effective space available, twice the DNS, divided by the space used by the process in the past, 6S. To illustrate these, we'll go to page 19 in the workbook. Operator 1. And down at the bottom of the page, we had 185 data. And after the last class, I calculated the average for operator 1 is 10.29. And the standard deviation statistic for operator 1 is 3.48. So I put all 185 data in the calculator and pushed the button. And this is what you get. Now, operator 1 had almost 26% non-conforming. He had a lot of non-conforming product. So his average is 10.29 and his standard deviation is 3.48. So let's do our calculations. P sub P P sub P upper spec limit minus lower spec limit over 6S. So that's 7.0 over 6 times 3.48. .34. So the space available is 34% of the space used by operator 1. Let's write that down. Space available . 34% of space used by operator 1. in the past. He's not likely to do much better in the future, however. Remember, his long-term average is 23% non-conforming, and he's got 26% today. So he had an average day. What's our DNS? Well, what's the average? 10.29. So 12.5 minus 10.29 . 2.21. So P sub PK twice the DNS divided by 6S. Well, that'd be 4.42. Three 3.48 times 6 is 20.88. Let's do that one in your head. 0.21. The effective space available is 21% of space used by operator 1. Okay, let's go back to the textbook then and talk about how these 4 indexes are related. Page 134. We learned last Thursday that if a process is predictable, method 2 and method 1 are going to converge to give about the same number. But if a process is unpredictable, method 1 is going to get inflated relative to method 2. So if you have an unpredictable process, your performance indexes are going to be smaller than your capability indexes. So the gap between the top tier and the bottom tier is going to define the gap due to being operating the process unpredictably. The gap between the right side and the left side will define the gap due to being off target. So as your process is operating closer and closer to the target, the right side is going to move closer to the left side. As you operate more predictably, the bottom tier is going to move up toward the top tier. So PPK, this is kind of your process where is as is. This is the life you're living in all its ugliness. This is the process potential. And the gap between PPK and C sub P is the opportunity that exists by learning how to operate the process predictably and on target. So when you have these four numbers, you can pretty well just tell the story. For example, middle of the next page, there are four examples I've been using through this chapter, which we haven't been talking about because I wanted to talk about them here. So here are the four numbers for the socket thicknesses. What can you tell me about the socket thickness process from these four numbers?
It's predictable.
It's predictable.
And
And it's on target.
And off target.
Even off target, it's still capable. 90%, essentially, it's going to be capable. So it's capable, predictable, and a little bit off target. Remember what Dave, the supervisor, said? It's time to retool and pull the average back up, which is exactly the right action. Bundling? Okay. What about the Creel yields?
Process is unpredictable and
They're a
off
basket
target
case, aren't
also.
they? Everything's wrong. Unpredictable, off target. I mean, somebody might say, CPK of 5138 is great. But you see, if it's not echoed in the PP value, then it's just hypothetical. The process has good hypothetical potential, but it's not operating anywhere near that, nor is it on target. What about the resistivity data part one? Now, the next set of ratios are smaller, but again, you have to interpret them relatively. 0.29 versus 0.42, and 0.22 versus 0.31. This process is unpredictable, and it's off target.
And not capable also, right?
But they found the assignable causes and fixed them. The story's on page 81 in the textbook. And after they fixed it, they're operating predictably and on target, and yet they're not capable. Predictable and on target, they're doing the best the process can do, but the best this process can do is about like the beadboard, it's not capable. You see, the four numbers together tell a story. We're going to utilize the graph on the previous page in reducing production cost. So we're going to come back and visit this afternoon. But this picture is a very important picture because it helps you to understand the relationships and what each of these numbers is telling you. This is unpredictable and off target. This is predictable but off target. This is unpredictable on target, and this is on target and predictable. I'm going to utilize that, as I said, this afternoon.